My name is David Rockstraw. I am the Robert Davis Distinguished Professor of Chemical Engineering and the Academic Department Head of the Chemical and Materials Engineering Department at New Mexico State University. I'm talking to you today from my home, the historic Rafael Bermudez home place in Mesilla, New Mexico, an historic adobe home that was built in 1875. I moved in 7 years ago, and this home has become essentially my passion for doing adobe research with Mesilla Valley Preservation. Today we're going to talk a little bit about measuring salt concentrations in adobe walls. Previous videos have demonstrated how to sample adobe material from walls. Today we're going to look at analyzing the salt concentrations within those walls. So our goal today is to develop a plot that looks like this. Along the y-axis here, we have the salt loading measured in grams of salt per gram of adobe sample. And along the x-axis here, we have distance into the wall. So essentially what this chart shows is how the salt concentration changes in the wall as we move further into the wall. In this particular analysis that we've done, you see that close to the surface of the wall, the salt concentrations are high, but as you move into the wall, the salt concentrations are reduced. In front of me, I have the tools that we're going to use to perform this analysis. I have a scale and I have a conductivity probe. This conductivity probe is a field conductivity probe. It's rugged. The probe itself is relatively rugged. It won't break, and it measures how electrically conductive a solution is. It measures conductivity in the units of Siemens. The Siemens is the standard international unit for electrical conductivity. For those of us that are a little older, you might remember when it was called the mho, M-H-O, which is ohm spelled backwards, where ohm is a measure of electrical resistance. Turning the meter on, it goes through its startup cycle. And upon completion of the startup cycle, we'll get a reading for the solution that we have the probe contained in at the moment. This is distilled water. Consequently, the conductivity of distilled water is very low. It doesn't have a lot of ions in it that will transport electricity through the solution. So we see that there's a reading of about 7 microsiemens, where a microsiemen is 1/1,000,000th of the unit Siemen. As we add salt to the solution, we will see that conductivity increase. The relative Siemen concentration will get larger. So the first thing I'm going to do is calibrate this probe. For pure distilled water, which is essentially free of any salts or ionic material, we get a very low readings, as I mentioned, 7 microsiemens. So to calibrate this probe, what I'm going to do is I'm going to use a standard sodium chloride material and some distilled water, and I'm going to make a solution of known concentration, and I'm going to measure the output on the meter. I have a single slide here that shows essentially the calculation that we're going to perform. The first step in the process is identifying this constant C. This constant C is a constant associated with the probe, the conductivity probe that we're going to use to make our measurements. We're going to multiply that by the measured conductivity of our sample, and then the final part of the calculation includes the mass of adobe and the mass of water that goes into our sample. So the first step will be calibrating this probe, calculating this constant C that you see here in this calculation. In order to calculate the constant C, I have to make a solution of known salt concentration. So in this first term here, you see the mass of salt that I add to the sample, the mass of water that I add to the sample, and the conductivity that I measure for that sample. So this will be my first step, is calculating this constant C by preparing a solution of known conductivity. So I'm going to dry out my beaker here. It's a little damp. I'm going to place this beaker on the scale And I'm going to tare the scale. Take a moment to start up. And so now I'm going to push the tare button to set it to 0. Now I'm going to take the beaker and fill it about 3/4, just enough to submerge the probe with distilled water. I'll return this to the scale. The scale is telling me I've got 89.78 grams of water. So I'll make a note of that. This is distilled water, so when I put the conductivity probe in it, I should expect a very low conductivity reading. And I see I'm getting a reading of about 1 to 2 microsiemens, so 1 to 2 1/millionths of a Siemens, very low conductivity reading. I'm now going to put this small beaker of sodium chloride. This is reagent grade sodium chloride from Fisher Scientific. More than likely table salt, Morton salt that you buy from the store will serve the same purpose. And I'm going to tare that beaker so that now as I pour salt out of this beaker, when I put it back on the scale, there will be a negative reading to tell me how much I've taken out. And I'm going to pour about 10 or 12 grams of this salt in here. Stir it up. After the salt is completely dissolved, I'm going to move my conductivity probe into this beaker and get a reading. And at the moment, I'm getting a reading of about 100 millisiemens. The probe itself has a range of up to 200 millisiemens. In that range, it has a linear response, meaning that for a given amount of salt, we get a proportional change in the reading all the way up to 200 millisiemens. So I would really like my calibration point to be close to 200 millisiemens without going over. So this tells me I'm about halfway there. So I'll remove the probe, put it back in my soak solution, add some more salt, stir it up. You can see I've used all of the salt. And by returning the beaker, I find that I have used 12.68 grams of the sodium chloride. So I'm going to make a note of that also. Make sure the sodium chloride is completely dissolved in solution. And return my probe. And without spilling, I'm getting a reading of 183.6 or so millisiemens. Give it a couple of moments here to stabilize. $173.1 millisiemens. So I'll make a note of that also. And that's the data I need to perform the calibration. The calibration constant is then calculated according to these notes I've made right here. The constant is the mass of sodium chloride that I added to my sample, divided by the mass of water that I added to my sample, divided by the conductivity reading that my probe provided, 173.1 millisiemens. So if I get a calculator out, that was 12.68 grams of sodium chloride divided by 89.78 grams of water divided by 173.1 millisiemens means that my calibration constant is 0.00081 0.59. And so this number will permit us to convert analysis of our adobe samples that were collected earlier in the day to an equivalent salt per gram of adobe ratio so that we know how much salt is in these adobe samples. And so now, based on the measurements we've done to this point, we've identified the calibration constant of this probe. We will use that calibration constant in the next video where we actually analyze the adobe samples using this expression at the bottom. We are looking for grams of salt per gram of adobe, our calibration constant times the conductivity of samples measured using the adobe samples times the ratio of mass of adobe to mass of water that we'll measure for those samples will be our next step.